Hello, my name is Jacob Hayes, and today I will be presenting about Lab 4, which is about bar magnets. So the purpose of this lab was to measure the magnetic field of a bar magnet at different distances, and then we would compare these values that we saw to those predicted by the PHYS law. So some preliminary results here. We found that N was negative 2.3832. And we also found that the magnetic dipole moment, mu, was 5.87 ampere times meter squared. So here are the fundamental principles involved with this lab. First one that I mentioned earlier is the Biot-Savart law. This law describes how a current element creates a magnetic field that depends on current, distance, and the direction. And you can see the diagram down there as well as the equation. We also need to know about the magnetic field of a magnetic dipole. So essentially, it decreases with distance and resembles an electric dipole field with lines looping from north to south, as you can see down there in that diagram there. And that is the equation above it to describe it. We also need to know about the distance dependence formula, which essentially just allows us to linearize our data, which allows us to better understand what's going on with the graph. So here's a procedure for the lab. First, we downloaded the magnetometer app, then compensated for magnetic north from the Earth, of course, and then we found the magnetometer chip in the phone. Then after that, we measured the on-axis and off-axis magnetic fields of the bar magnet. And you can see the pictures there on the right of what it kind of looked like. And here's the actual picture of what it looked like. In the system was the magnetometer, which was within the phone, and the surroundings were the bar magnet. So here are the results from the on-axis measurements. As I described earlier, the graph is linearized through the use of the natural log, and the slope right there, negative 2.3832, was the n that I talked about earlier in the brief preview of the results. So nice linear graph there. So here are the calculations that were performed for the on-axis measurements. In the top left, you can see the distance dependence formula being utilized. And then on the right, you can see how mu was calculated through the equations and work shown there. So here are the results for the off-axis measurements. Very small values, of course, for all of these, as we're working with microtesla. So keep that in mind. So here is the computational model that was used. You can see on the left there was what we found was the mu mag, which is 5.87 amperes times meter squared. And then those are some key functions there that are very important to know for how this computational model worked. There on the left, as you can see, the formula for magnetic field, which is the B equals equation. And we can see on the right the diagram of what the magnetic field looks like at different locations. So here are some of the assumptions made. We assume the bar magnet behaves as a magnetic dipole, and we also assume that there is no magnetic interference from surrounding fields, like maybe outlets or something like that in the room. So some possible sources of error include rounding errors in calculations, also inconsistent orientation or placement of the phone, nearby magnetic fields, and also the magnetometer app being inconsistent. So what if the experiment wasn't oriented to compensate for the magnetic north, and instead the meter stick was laid out at some intermediate angle with respect to Earth's magnetic field? How would this change our results? Well, if we did this, Earth's magnetic field would actually act as a magnetometer, and the slope wouldn't be right for our measurements. So that would all be because of it not accounting. It would be wrong because it accounts for the Earth's magnetic field in addition to the bar magnet. So what if it were possible to stick two identical magnets together end to end, which we know we can't do, but for the sake of the argument, and then run the experiment again? How would measurements be expected to differ? Well, the magnetic moment would actually double here, since B is proportional to U. And since B is proportional to U, B would double as well. And thank you for your time and attention to my presentation.